Hi, good morning, everyone, and welcome to the second Aurora project webinar about blockchain and tracking devices. My name is Sara Tana. I am the dissemination manager of Aurora project, and today we are here with two different speakers that will present their activity inside the project related to blockchain and tracking devices. Our first speaker of today is Sanjeev Kumar. Sanjeev is a PhD as a PhD in electrical and electronic engineering from University of Cork in Ireland, and now he will give two different presentations. One will be more theoretical and one will be more practical about embedded wireless tracking for indoor localization. I remind you that this webinar is recorded and that you can see and have a look at this webinar also on our Aurora website. I just kindly ask you all also to turn off your camera and turn off your microphone. Many thanks, and Sanjeev, the stage is yours.
Thank you so much for the introduction, Sarah. So I'll share my screen now. Okay, so good morning, everyone, and welcome to the webinar on blockchain and tracking device. My name is Sanjeev Kumar, and I work with Wireless Sensor Network Group at Indian National Institute, Cork, Ireland. And in this webinar, I will be presenting our work on tracking device. Then Matias Torres Diaz from AVVALE will be talking about blockchain solutions. So just briefly going through the agenda that we have today. So first of all, I'll provide a brief introduction of Aurora project. Then I'll be talking about theoretical aspect of indoor localization system using ultra-wideband technology that we have developed here. Then following to that, we have a practical demonstration of the tracking device that we have developed. After that, we'll have some time for taking questions related to tracking device. After that, we'll have a short break for 5 minutes. Then I will invite Matias Torres Diaz from AVVALE for his talk on blockchain solutions. So going through briefly about the details of Aurora project. So the full form of this Aurora project is artwork, unique recognition and tracking through chemical encoded data, miniaturized device and blockchain alliance. To talk about the granting authority, so this project was granted by European Research Executive Agency, and this project started on 1st January 2023, and the duration of this project is 36 months. So it means it will be finishing by the end of this year. And we would like to thank European Union for its contribution for approximately 3.47 million euros for this project. Here we have the project partners all from Europe involved in this project. So firstly, we have AVVALE, then B. Warrant, CSGI, University College Cork, OTID, Indian National Institute, Antonio Mirabal, Hungarian National Museum, Balkan Museum Networks, and Lviv Polytechnic National University. So talk about the key objective of this Aurora project. So the main objective of the project are to explore the feasibility of a non-destructive, practical, cost-effective and efficient solution for artwork authenticity verification process and tracking. And we are looking forward to pave the foundation to achieve an advanced non-invasive art piece countermeasure system against illegal activities which targets cultural heritage. For Aurora project, we have 3 main technological pillars. First pillar is chemical research on nanomaterials. This is mainly for anti-counterfeiting process. Second pillar is wireless tracking device, where we basically talk about indoor localization system using ultra-wideband technology for tracking of museum artworks. And lastly, we have third pillar, which is blockchain-based digital tool for data security. Okay, so I'm going to talk on tracking device, and in particular, I'm going to present our work on the development of an embedded wireless tracking device for indoor localization. It is maximum. Yeah. Okay, so before starting the actual technical thing, I will explain. Explain that our research institute, which is Tyndall National Institute, based in Cork, Ireland. So, research at Tyndall National Institute converges, micro and nano electronics, photonics, and advanced materials, and with over 600 people from 52 nationals. The research at Tyndall National Institute impasses its compass on different areas, including agri-tech and food security, health and life sciences, micro and nano energy, and information and communications. Particularly, I work with Wireless Sensor Network Group and Tyndall National Institute. Is it all okay? I think it is. But it is a maximum of my end. It is fine. It is fine.
Everything is okay, Sanjeev.
Yeah, I was just wondering, is the screen clearly visible there, or?
Yeah, clearly visible, and we hear you very well.
Okay, yeah, thank you so much. Yeah. So at Wireless Sensor Network Group, we are specialized in developing low-power, state-of-the-art wireless sensing solutions for next-generation IoT applications. Now, we'll talk about the actual problem that we are addressing in this project. So the main challenge here is how to localize indoors. So here what we want to localize the movement of cultural artworks in real time. If there is any movement, we would like to track the movement of these artworks. And we would like to thank Hungarian National Museum for providing these pictures and floor plan on the right side in here. So that, and here what we want to look at the tracking device, which will be artwork, and see how it moves in real time, so that we can control the counterfeiting things and any theft attempts by criminals or so. So the first question might come in my mind, that why can we not use global positioning system? The GPS works completely fine outdoors. For example, we use Google Map. Wherever we go, we use our mobile phones, and we look at our location in real time. But we cannot use GPS indoors, mainly because building walls and roof, this prevents the RF signal, GPS RF signals that comes indoors. That's the challenge. We cannot use global positioning system technology indoors. It means we need to have another technology that can be used indoors. And we did a lot of research and looking into current commercial solutions and research publications, and we came to know that for indoor localization, currently ultra-wideband technology is one of the most accurate system that can provide localization accuracy in under centimeter level of accuracy for real-time indoor positioning technology. And here we have briefly show the concept of indoor localization using ultra-wideband technology. So you can see here we have a map of large room, and what we do for indoor localization, that we place anchors denoted here as A1, A2, and A3 at different corners of the room at known location. And here this T represents the tag that will be attached to an artwork. Then this tag starts communicating with anchors using ultra wideband pulses, and by doing this communication, it calculates the distance between anchor and tag, and finally using the trilateration mechanism or algorithm, it calculates the real-time location of the tag. So for ultra-wide localization, the first thing is to calculate the distance between this tag and anchor. As explained, we have tag in the center which will be attached to the artwork, and we have multiple anchors. So here first step is to calculate or find the distance between tag and anchor. So tag here is represented as initiator, and anchor behaves as a responder. If you look at the plot figure here, so what happens, the first tag starts giving a polling ultra wideband pulse signal to anchor. Once received at the anchor terminal, this anchor processing of the received ultra wideband packets and then return its back to the tag. So here we have two important time parameters, which first is T round and the second is T reply. So T round is the total time taken from the start of the signal transmission from tag and until when it received back at the tag again. And here T reply represents the time taken at the anchor or responder end for the ultra wideband received data packet processing. Then we calculate the distance between tag and anchor using time of flight value, which is actually we take the difference of T round and T reply divided by 2 to calculate the time of flight. And finally, we calculate the distance d between tag and anchor by multiplying this time of flight with the speed of light. So this is how we calculate the distance between tag and anchors. And once we have the known values of because we already have the known values of locations of anchor, that what location they are installed, and now we have calculated different distance parameters like d1, d2, d3 in here, d1, d2, d3. So once we have these parameters known, we apply trilateration method to calculate the real-time position of the tag in terms of XY coordinates. Now we have developed an embedded hardware prototype that I'll be showing in coming slides. So here is the architecture that we have implemented for this real-time localization of artwork, and we call it tag, or even we call it embedded wireless tracker. So if I quickly go through the architecture, so I will be showing the different key components or units that we have on the tracker. So first is ultra wideband module, which we have used for indoor localization. Then we have a DC-DC converter for voltage regulation. And here in the center, we have microcontroller unit, which is basically an ARM Cortex M4 microcontroller unit. And the key benefit of using this microcontroller unit is that it has integrated radio transceivers like LoRa and Bluetooth Low Energy. Then here we can see the sensor unit. So here we have environmental sensing IC that can perform sensing for temperature, relative humidity, and light. Then in the center here we have RTC, which is real-time clock. So the function of this block is to keep track of the processor and different units on the tracker, even if the power is turned off. And then here we have energy harvesting IC feature for solar and radio frequency energy harvesting. Then we have a receiver unit to wake up the system from the sleep mode. So this feature, these two or wake up receiver feature, we have implemented to overall reduce the power consumption of the system. And then this block is the accelerometer, which provides alert for any movement of the tracker device from its actual position. As we know, development of embedded system requires two main aspects. First is a schematic and second is layout. So here I have shown the key blocks that we have implemented in our schematic. And we developed our embedded hardware system using Altium Designer PCB environment. And here we can see the key blocks like microcontroller unit, then ultra-wide module, RTC real-time clock, accelerometer, and environmental sensing blocks. And we have more blocks, but I'm just showing the key blocks out here for the just to represent for the presentation. And on the LTM designer platform environment, we can see the PCB layout here. So here we can see the key blocks like ultra wideband module, microcontroller unit. These things I'll be explaining in coming slides. And here we have, so we got, after designing the layout, we finally sent our design for fabrication. And here we have the photograph of the final prototype. We can see all the key components in here. For example, here we can see the ultra wideband module. Then we have MCU, microcontroller unit with integrated LoRa and BLE. Then accelerometer, real-time clock. Here we have temperature and relative humidity sensor. Then light sensor. Here we have wake-up receiver to for power conservation. Then energy harvesting unit. Then we have some reset button for real-time clock and microcontroller unit. Here we have plug for connector for programming and debugging. So these are the key blocks, and here we can see the developed prototype. And on the right side, we can see the bottom view of the prototype that we have developed. Now talk about the tag configuration and payload. So at the moment, we have configured our algorithm in such a way that the tag transmit its data every 15 minutes when it is not moved. So it will be sending distance information and sensor information like temperature, battery voltage, relative humidity, all these parameters every 15 minutes when it is not moved, means when it is in a static mode. However, when it is moved, the the tag starts transmitting data continuously. And here we have the details of all the payload that we are transmitting. So it transmit payload like device ID, event ID, battery voltage, temperature, relative humidity, illuminance for light sensing. Then we have anchor ID, distance information using which we calculate the actual position of the tag in real time. And we keep some reserve bytes also if we want to incorporate something in future. So we have some reserve bytes as well. Now, as I mentioned, we have developed the tracker, which is very low power consuming. So here we can see on the plot, plot we have power consumption profile. On the bottom side, we have the time in milliseconds, and on the y-axis we have power in milliwatt. So if you look at the power consumption profile, if we can see once the device is turned on from the sleep mode, it has a typical sample duration of 34 milliseconds. And here is the boot duration when all the device components turns on from the sleep mode, and it consumes I think approximately 170 milliwatt of power for boot time. And then these two peaks represents when the ultra wideband module and LoRa module turns on, and these three coupled spikes for this shows two-way ranging for transmit receive, and transmit receive. So these three pairs of single-sided two-way ranging shows for two-way ranging power consumption. And the end here, the last peak represents the data transmission from LoRa module to the coordinator that we have for sending the data finally to the cloud. And in sleep mode, this is the key benefit of this tracker, that in sleep mode, this tracker consumes very low power of 2.4 microwatt. So that's a really good number that we achieved. And in active mode, a typical sample consumes of 121.26 millijoule of energy if there is no retransmission required. And now once we have all the data available on the tag, so now we would like to send that on the cloud or the Things network so that it can be available on the server that can be accessed online. So as I said that this tag communicates with anchor. So we can see here we have anchor 1, anchor 2, and anchor 3. So tag sends ranging request and then anchor answers. And using two-way ranging technique, we calculate distance d1, d2, and d3, and then the all those information, distance information and sensor information are transmitted to a coordinator, central coordinator unit using LoRaWAN. And finally the LoRa, using the LoRaWAN technology, we send our payload to LoRa gateway and finally to the Things network. And once the payload is available on the Things network, our partner AVVALE utilizes these sensor parameters and distance information for blockchain security and data visualization. Now, once our hardware part was developed, then we performed the real-time demonstration. And for that real-time demonstration, we have the key hardware unit that we implemented. So here is the tag, top view of the tag we can see, and here I'm showing the internals of the tag. Then we have implemented 3 anchors and the coordinator we can see in here. And finally, we have a LoRa gateway to send our data to the Things network. And we performed our indoor localization demonstration in a Tyndall National Institute library, and this is how we have set up the demonstration. So we can see at the one of the corner we have our coordinator represented at C1. Then we have placed anchors A1, A2, and A3 at 3 other corners of the room. And here on the right side we can see how we have mounted our anchor or coordinator using a tripod. And our shortly I'm going to show this live demo as well, where my colleague will be moving the tag and we will be able to see the movement of the tag on a GUI in real time. So this is how we are going to do it shortly. So we will be showing a GUI, and here the four triangles or at the room corner represent 3 anchors and 1 coordinator, and this red big circle represents the tag. And along with the tracking of the device on the GUI, we can also see the parameters like temperature, relative humidity, battery voltage, and time, etc. Now, talking about the accuracy of the indoor localization. So for that demonstration setup, we installed our anchors at known location, and we measured the tag locations at 6 different specific XY coordinates. So we can see we put our tag at different known locations like 200 centimeter in X and 100 centimeter in Y. Similarly, we put at 200 and 200, 200 and 300. So using these different value of coordinates, we took the measurements of tag location in 6 different specific coordinates. And what we found is the really great number here. So we can see for all the measurements that we took, we were getting a accuracy between what value of location we expected and what we actually achieved. So for 100% of our measurements, the accuracy was better than 20 centimeter. So we can see the numbers here. The worst accuracy that we achieved was 17.5 centimeter, and the best that we achieved was under 3 centimeter. So that's the really good number. So best case scenario is 3 centimeter, worst case scenario is 20 centimeters. So these are really good accuracy, specifically when we compare with the literature where people claim 30 centimeter, 40 centimeter, and more specifically, if we talk about our commitment for this Aurora project. So in the description of work, we had promised that we will be delivering a tracking device which will achieve a localization accuracy of 50 centimeter, but we are very happy to say here that we have achieved a much better accuracy of 20 centimeter. Now, once data are measured, so we wanted to transfer those payload to the Things network so that our partner AVVALE can utilize those data for further blockchain security implementation and data visualization. So here I have shown the data on the Things network. So we can see the live data here, and on the right side we can see the payload details as well. So maybe I will try to open this link. I'll see if opens so that we can see in real time that what is happening. Actually, to save the time, I'll open the tab I have already opened here. I will go to okay. Yeah, it is a little slow, but it's opening. Yeah. Okay, so we'll go here to so this is the device that we have called Aurora tag, and then we'll go to live data. So we can see, so currently it's 10:26 a.m. here in Ireland, and the data was updated, I think, yeah, 8 minutes before. As I mentioned earlier, the data, when it is the tag is not moved, data is updated every 15 minutes, but it can be changed as per our requirements. We can set this to 1 hour, 20 hours, 24 hours as per our requirements. So at the moment we have set this for 15 minutes. So it updates every 15 minutes. If I'll go further in, so here we can see all the payload details like anchor IDs, battery voltage. For example, we have battery voltage of 4.2 volt at the moment. The distance information using that two-way ranging technique. Then we have relative humidity number, temperature, all these parameters we can see live on the Things network. Then going to the slides again. And along with showing our payload on the Things network, we have also implemented live sensor data visualization using data cake. So we can see here all the sensor parameters. So I would also like to show this online implementation that we have done. Okay, so and this data can be accessed from anywhere in the world. So that's really good implementation we have achieved. So wherever tag is placed, we will be able to see the sensor information in real time. So we can see this Aurora tag, and here we have temperature, relative humidity, light, then ultraviolet index, infrared, and battery voltage. We can see all these numbers are updated 10 minutes before, and after 5 minutes it will be updated again. And also we have implemented this waveform to show for better visualization. At the moment it is showing data for last 1 week, but it can be said if you want to keep track of last 1 month of data, that can also be implemented. So this is really good visualization of the sensor data that we have developed. And then next week we are planning to deploy our system at 2 places in Cork, Ireland. So first deployment we are planning for Cork Public Museum, Ireland, and second deployment is planned for Glocksman Museum, University College Cork, that we have planned for the next month. Yeah, early next month. And we have planned for the final deployment in Hungarian National Museum. So we are planning, and discussions are going on that how we are going to implement and deploy our system on Hungarian National Museum. So we will be updating you guys in future that how it proceeds. And now we are going to showcase our real-time live demonstration of the tracking system that we have developed. So my colleague Jara is going to share her screen now so that we can see. I will stop sharing and she will start sharing so that we can see how tag moves in real time and tracks the movement. Okay, so now you can see Jara is taking the tag in her hand, and looking at the left side in here, as I showed before, this is the GUI that we have developed. On the four corners, we have 3 anchor and 1 coordinator, and the red circle represents the tag. Looking at the right side, we are showing the real image, real video of the room, the library where we are currently demonstrating this technology. So the Jara is currently standing close to coordinator C1. Now she will start moving, and then we will be able to see the movement of tag. So now please start moving. Now she is going towards anchor A3. Now she is towards anchor A4. She is close to anchor A2 now, and she is going in toward the center of the room. That's good. Yeah, we can see the good coordination between the GUI and the real-time movement of yours in the room. Yeah, so that's the really good demonstration of the technology that we have developed. So maybe you can stop sharing, Shara. And yeah, so that's the demonstration that we have. And now I would like to invite our partner, Matias Torres Diaz from AVVALE. No, before that, maybe if you would like to have, if anybody has question, we would like to take that. And then I would like to, then we'll have a break for 5 minutes. Then Matthias will present his talk on blockchain. Thank you very much.
Does anyone has any question? If you has any question, please write in the chat. We see here a question, Sanjeev. From what I gather, you need 3 anchors in every room in the museum if you really want to track the objects hereabouts in the building. So what is the practical use for this excellent prototype?
Yeah, so the practical use is, that's what we have been working on. So once we suppose we have an artwork that has a threat of being stolen, or so we can attach our tag to the artwork, and then we using this system, the communication between tag and all the installed anchors, we will be able to look at the movement of the tag in real time.
And the same person asked, how would you attach the tag to an object?
No, so this is what we are discussing with our museum conservators, and at the moment, it depends on the size of the artworks as well. If, as I showed, if I have a big box of the gilt chest I showed, we can make some, honestly, it needs to be discussed with the museum conservators, because they are very much concerned and very protected about their artwork. So at the moment, the size of this tracker that we have developed has a size of approximately close to credit card. So honestly, it cannot be placed on paper, but it can be attached to a big sized artwork.
Okay, many thanks. If someone has any other question, please, you can write in the chat. But I don't see any other question at the moment. Okay, so no other questions, Sanjeev, for the moment.
Yeah.
If we are ready with Matias, I think that we can go on. Good morning, Matias.
Good morning, everyone. Hi, I'm Matias, like I said before, Sanjeev. I'm from AVVALE, and I worked on the blockchain team. And today we are going to present theoretical to practical webinar on blockchain. Okay, so I will say, Sarah, probably I will show very short introduction of what Sanjay have showed, and after maybe we can take a break before to start with the theoretical and practical phase, so we can follow the
stage is yours.
The outline. Okay, thank you. So I will share my screen. Here we are. Okay, let's start from here. Sanjay, what was showing? He showed that if they move the tracking device, they can see in real time the device is moving. All the payload is sent to AVVALE. We work that payload and we store in a database. We store it on EPFS, which is a interplanetary file system, is a decentralized storage system. And also we save it on blockchain. At the same time, when the device is moving, so when the artwork is moving, we receive an email. So those emails are from some minutes ago. For example, these one are the latest when Sarah was moving the tracking device. So we have real-time email and login system inside AVVALE. So we keep track of all this artwork. We have a link to the artwork, which was moving. So I will start from this point to show you how we can see it on Aurora. So let me move this. This is the back office page of Aurora, where we can have our artworks, collections, and some other features that we are not going to see today. But going on artworks, now let me reload the page. We can see all our artworks. In this case, in this specific case, we are looking for, sorry. I'm having some trouble with the connection today here in Turin, where I live. Is very hot outside, so there are several problems with internet connection and electricity. Let me see if now is loading. So, okay, we left it to go there. This is Etherscan. Etherscan is one of the hundred of tools we have to track blockchain. This is a public tool, so everyone can go to Etherscan and check for each transaction on blockchain. We are going to look further on what is a transaction on blockchain later. But you have to note that one a transaction is in a blockchain, it cannot be changed. So it cannot be tampered, is a proof of insurance, is very, very secure. And in this case, when the artwork is moving, AVVALE receives the payload, elaborate, and store it on the blockchain. When we store some data on blockchain, we emit an event. In this case, we emit 3 events, okay? The before execution, user operation event, and the update position. The update position contains 2 topics, which is the token ID, so the artwork identification, so we can know what artwork was moved, and the CID. This is an identification for EPFS, like I said before, so we can see the payload. In this case, is encrypted, so we cannot see it clearly, but we in this string of code we can access to the payload and see the position changed. At the same time, from the Aurora back office, we can see the same data in a better view. So let's say we are taking this artwork, this one, we can go on view options. As you can see here, let me zoom it. We have manage telemetry tag, which are some options to the telemetry tag, the anchor that Sarah was moving before. And if we go on history, we can see the history of each transaction made on this specific artwork. So in this case, we have 30 transactions. But if we go at the first one is the creation. So when the artwork was created, a transaction was emitted. And as you can see, we can click on see transaction there. We are opening Etherscan. We are putting the transaction hash here. And we can see all the data that was moved, how much gas we spent, the token ID, okay, of the Aurora collection, and we can see logs. As you can see here, we have a lot of logs. The one we are interested in is the transfer. So when the transfer is emitted, we know that NFT, in this case, is emitted or transferred. Here we can see 3 topics from, in this case is 000, so we can understand that the address the NFT was created, to the address where the NFT were sent, in this case is the address of the museum, and the token ID, so the same token ID that we are seeing here, the 6, no? This one. And we can see here all the other metadata changes. So for example, if I change some metadata, I add some photos, some pictures of the artwork, is everything stored here? So I can have an historical chronologies. And as you can see here, we have the position change 10 minutes ago. So when Sarah were moving the tracking device, and we have the some additional data, like I said before, is encrypted on this type of transaction, but for the back office we can decipher it. So here we have the distance from the anchor point. On the back office we have another page where we can see more data like humidity, temperature, battery voltage, battery status, and so on. So this is the start, now the end of the presentation of Sanjeev, to see how works the tracking device, how they move it, and how we store the data, we handle the data, and so on. If anyone has any question, please do it now, because after a break, we are going to start with the theoretical phase, and after with some practical playground phase. So if anyone has any question about what we are seeing here now, what I have explained.
Yeah, we have a question.
Yeah.
How the system works while moving objects for exhibitions, for conservation purposes in the storages, and in case we are sending it for external loans, can we deactivate it temporarily?
Yes, it can be deactivated temporarily. We have handled several of these hypothetical situations, for example, on a loan. So as you can see here on the right, on the left side, we have loans. So we can exchange the artwork with other museums, or for an exhibition, a temporary exhibition, with, for example, a private owner, and so on. So it can be deactivated. It can be handled, for example, for some restoration on the artwork itself. Well, that's it.
Okay, many thanks. Someone has any other question? I cannot see any other question in the chat. Okay, I think not at the moment.
Yeah.
So we are going to take a little break. 5 minutes break, right? Okay?
Yeah.
So 5 minutes break, and then we start again with Matias' presentation. Thank you.
Okay. Thank you. See you in
Thank
5 minutes.
you.
Hi, Matias, if you are ready,
Yeah, I'm
we
ready.
can
Let
start
me.
again.
Oh, so yeah. Okay, so like I was saying before, now it's time for the theoretical phase. I hope it will go very, very smooth and fast. So let me see here. Okay. Because these are some Aurora projects information. So, but here we are. There are five, which is yeah. Okay, so introduction to blockchain. As I was saying before, this is going to be a very short theoretical phase because I want to concentrate on a more more practical phase. You can find some very, very good content and of high quality on internet on what blockchain is, how it works, and since there are hundreds of blockchains around the world, we cannot study all the technologies they have. So what blockchain is? The first conception of blockchain was introduced in the early 90s. So there was an idea of create some sort of a block, no, is some sort of chain of hashing function. We are going to see everything later. So in the early 90s, there was this introduction to blockchain, which was not called blockchain, but was some raw idea about it. It was elaborated in the years, and in 2008, as Satoshi Nakamoto, we don't know who he is, if he's a single person, a group, we don't know nothing about it. We just know that his pseudonymous is Satoshi Nakamoto, publish a white paper, is still available on the internet, on a forum. In this white paper, he was elaborating the concept of blockchain. So creating a transaction, in this case, economic transactions, so to move money, and group them in a block. And each block will be linked to the next one with a random phrase, okay, which is a hashing phrase. So we can have the insurance that it cannot be tampered or edited in any way. So for that reason, we say that blockchain is secure and cannot be changed. The data inside the blockchain cannot be changed. Otherwise, we can see it immediately, no? And we can create forks and other stuff, but keep it simple. Satoshi Nakamoto has this idea of property. Okay, he was saying in the paper that if we don't have our money, we don't have it, because if we put the money inside the bank maybe can block the our money. The maybe some taxes can be withdrawn from it. So Satoshi Nakamoto was saying. I want to have my money. I don't want to have any intermediary that have the money for me. So the bank in this case, and I want to be free to move the money without asking to someone else, like I said, the intermediary and so on. Uh, and it burns the year later. He launched the Bitcoin, which is the largest and most famous blockchain. I think every one of you knows what is Bitcoin. And after the launch of Bitcoin, it takes several years to start being using from a very high group of people. And in 2014, this 18 years old a Russian guy, Russian dude, Vitalik Buterin, was a concept, another idea. He said, okay, it's cool, Bitcoin is cool, but we have several limitations on it because it's low. It can be only used, it can only elaborate 10, 15 transactions per minute. So if I need to send money, it can take maybe some 15, 30 minutes to be effectively sended. So it's low. I want to have more freedom to move, for example, other type of data. So he published a white paper, okay, of Ethereum, which is the second most famous and largest blockchain. And he talked about the smart contracts. So the possibility, since the blockchain, like I said before, has some intrinsic technologies that prevent tampering and contrafaction and frauds, he was thinking we can run on blockchain some smart contracts, which are simply the code, some codes that is executed on blockchain. So we can have insurance of what is written inside the code. Let's say, for example, if I want to buy some used stuff, I go to eBay or maybe Amazon, and I track the, I don't know, the bike I want, I need, and I buy it. Amazon, for example, takes charge of it, is the intermediary in this case. It keep the money. The seller sent to me the product I want to buy, and after I receive it, I don't make any complaint. Amazon send the money to the seller. Okay, so this is how it works usually. With smart contracts, we go further and remove Amazon, so remove the Amazon fees and any other intermediary fees, because we can write a smart contract where I can say, for example, I can put the $10 on the smart contract, and when you send to the smart contract the NFT token, everything I want to buy, it will unlock for you the money and for me the product. No, so we remove the intermediary. This is just one of the severe things you can do with smart contracts. Nowadays, the evolution of blockchain is not on the technologies you have inside a blockchain, but is in the technology that builds the blockchain. Because how we are going to see later, run a blockchain it can be very expensive. So now several entities has moving from adding new features to blockchain to trying to build the most efficient blockchain. We are talking it in a bit. How the blockchain works, no? So we're talking about blockchain when it's born, what it can do, very raw way. How blockchain works. I was saying before that there is a cryptographic hashing in this case, which is a fundamental blockchain technology. What is a cryptographic hashing? Is a function where you can send anything you want. Let's say, for example, a string. Okay, I can send an entire book. Okay, and it returns to me a fixed string of characters which are random, and this string is called hash. And if we go and change even a comma or a white space, the hash will completely change. So let me show to you an example of hashing online, so it can be more clear for you. So there are several standards. One of the most famous is the SHA-256. Let's say, for example, I write here hello. Let me zoom it for you. Okay, so I write hello, and this is the output. This is the string, fixed string of random characters. Let's say, for example, I change a comma. Let's see, it changed completely. Okay, So if, for example, take a book paragraph, a random book paragraph, let's say, for example, take this one, okay, which contains several characters. As you can see here, this is the output. Let's say I change just a point, it changed completely. And for example, I changed this point here, it changed again. So the possibility of collision, so when two hashes, two outputs hashes are the same, are mathematically is possible, but for our definition of what is possible is not. Okay, there are less atoms in the universe than the possibility that two hashes are the same for an input, a different input. So this is how blockchain works. So when I send, for example, a money, some data, it is hashed. So we have the fixed string, the random fixed string, and is added in a block. Okay, this block is hashed the same way and is linked to the next block. So in this way, we can know for sure that the data inside the previous block has not changed, because as how I showed before, if we change a comma, it changes completely the hash. So we can have proof that nothing has been changed. So let me start again the presentation. Okay, so the transaction is initiated from the user. So I send, for example, some data to the blockchain. A block is created. A block is a simple, just a box, okay, where someone put inside transactions. Let's say we call it pool transaction, because let's say there are 100 users that send at the same time a transaction. I am a validator, so I made the block, and I can put inside the block, let's say, for example, just 10 transactions, like on Ethereum, like on Bitcoin, and I choose from the transaction pool, from the 100 transaction, I can choose only 10. I will go to choose based on several parameters, and I will create this block. After I create this block, I send it to other validators that check the integrity of the transaction, because, for example, there are some transactions that are not valid, because I'm saying that I want to withdraw more money than I have. That is not possible. So for that reason, I have to do some checks before to build the block, because if I send a non-valid block and so is rejected, I will lose money, because I have used time, electricity, power computing to make the block. So I'm trying to be the more secure about what I'm putting inside the block. So once is validated, the block here is added to the change. So is linked with the other blocks through the cryptographic hashing, and the cycle continues. And so block after block after block, every single block is linked to the before one through this hash change. How a block is validated? No, it depends on the blockchain. Like I was saying before, there are hundreds of blockchain, and the technologies that are evolving now are on how blockchain are made. Because the most famous Bitcoin, we know that consume a lot of electricity, because blockchain use a type of consensus, which is a different type. There are several types to validate a block. Okay, the first one, the most famous, is the proof of work, which is POW here, POW, which is used by Bitcoin and was used by Ethereum and many other blockchains. This is we can say, the original consensus mechanism. How it works? A proof of work simply requires a proof of work. So I have a computer, the blockchain emits a random number, and my computer has to do some mathematical puzzle, some cryptographic complex puzzles to receive that number, okay? And the blockchain itself, in this case Bitcoin, try to make it harder or less harder to keep it on the range of 10 minutes to resolving a single puzzle. So what it means, if I have a very cheap computer, it can take for me hundreds of years to resolve a puzzle, because nowadays there are very big companies that have these gigantic office with millions of worth of computers to resolve the puzzle. And for that reason, to build a successful and valid block, I can spend around 25,000 of dollars of only electricity bill to build one single block of Bitcoin and to receive a recompensation for that. So nowadays, trying to resolve a Bitcoin puzzle is very, very complicated because it requires a lot of electricity and a very, very high-end computer. Many high computer, so it requires an starting effort of money very, very high. So for that reason, and for the CO2 complementations, some other blockchains were born using a different type of consensus, in this case, proof of stake, POS here, the second one. This is the second one most famous. Nowadays, almost every blockchain has moved from proof of work to a POS or other type of consensus. Bitcoin has not moved yet because Bitcoin hasn't a company behind. Okay, it's the community that keep it alive, and so to change Bitcoin, the majority of the community, the 51% of the community, has to do the change, and it will be not possible because at the moment it's very, very variegated, the community of Bitcoin, and it is not possible to change the proof of consensus. Ethereum, the second most famous, has a foundation behind, which is called the Ethereum Foundation, which makes several changes, improvement to the blockchain based on the community feedbacks. And they changed it from proof of work to proof of stake around 3 years ago. And what is the benefit? Low energy, because a proof of stake is very, very power efficient, since it not requires a computer to run it, a puzzle. So you can just have an wallet on your phone, for example. So less electricity means no computer, because there are very, very few cases that you need a computer to run a blockchain, because you don't have the puzzle to resolve. And how it works? Well, proof of stake requires an amount of money. Like is written here, you have to put in stake some money. Let's say, for example, on Ethereum now you have to put 32 Ether, which is the native token, on stake to be a validator. So nowadays I just have to buy some token, put it in stake, and I'm a validator. I can be one of the several validator. Higher is the stake, the amount of money I put on stake, higher are the chance that I will be the validator. When I am the validator, also when I choose the block that has to be to the next one to add to the change, I receive a compensation in money. So there is always some type of reward for who is committing in this kind of consensus. There are other types of consensus of mechanism, which is the delegated proof of stake. Let's say, for example, 32 ethers, for example, are a lot, are like $6,000. So let's say, for example, I don't have $6,000. I can delegate it to someone else I trust. There are several ways. So another type of delegated proof of stake is this one, the delegated proof of stake. The proof of authority, this one is very unique. I like it a lot, but it requires a permissioned blockchain. Let's say blockchain are basically free entry. Everyone can enter in a blockchain. Everyone can do a transaction. Everyone can be a validator. Okay, you have just some requirements, but everyone can do it. There are and this type of blockchain are called permissionless because it doesn't require any permission. There are a few types of blockchain which are called permissioned because are maybe some consortium blockchain. Let's say, for example, in the United States, Microsoft, Google, and Amazon decided to build a blockchain to share some type of data. And they don't have to spend any money, because why they have to choose a proof of work or a proof of stake, since they know that their blockchain will be used only by them. So they can choose a mechanism of consensus called the proof of authority. So you don't require any specific computational power or any stake to the validator, because you know the validator. So you give to him the authorization to build the next block because you trust him. Okay, let's say Amazon trusts Microsoft, Microsoft trusts Meta, Apple, and so on. So they have something in common. They trust each other. So the proof of authority is the most efficient and fast type of mechanism of consensus, but it is usually used on the permissioned, so private blockchains, because I have to know which is the validator. The practical Byzantine fault tolerance is used, for example, from a very unique blockchain, which is called Zilica, is used in Asia for the most, and it requires that the 61% of the validators, because everyone in a practical Byzantine fault tolerance, everyone is a validator. So I have to have a computer, even cheap, it doesn't matter. I can be a validator. And so every single validator have to validate the block. So let's say, for example, I build a block, I send it to a validator, to the next one, and so on. So it's cheap because it doesn't require any computational power, just very, very low computational power. It doesn't demand that I buy some tokens, so I put in stake my money, but it's very, very slow. Let's say, because, for example, if I have 600 validators, I have to wait that every single validator validates the block. And it's called practical Byzantine fault because I just need the 61% of the validators are good validators, so they are effectively rejecting the bad blocks and approving the good ones. So for that reason, it's called Byzantine fault. And for last, we have proof of history. Proof of history is, in this case, very unique because at the moment only Solana use it, and it works with hashing, like I was saying before, a hashing function, but on timestamp. So based on the time, is a very, very, very complex consensus mechanism. For that reason, is used only by Solana. The good side is that it's very, very, very fast. you can send hundreds of thousands of transactions per second on Solana, and it can elaborate it. The downside is that sometimes is too good that it can be attacked using a DDoS attack or other type of attacks, and simply it shut down. So Solana has shut down the blockchain like 7 or 8 times in the last few years. So it's very, very fast. It has some downside. So in the world, you are going to see POS. The proof of stake has the majority of blockchain. So this is the theoretical phase. You know, it's a bit maybe overwhelming, but like I said, online you can find a very, very high quality content about it, and I think this PowerPoint will be shared with you as well. You have the registration of this live as well too. So before to going with the practical phase, maybe someone has any question.
We have some question in the chat, Matias.
Okay, let me see. Maybe
So,
I can. Oh.
Do you want I read them?
Let's see. We can maybe see here, and they are in the chat. Okay.
In the chat, yes. Luca asked, very interesting application, the idea of monitoring artwork positions in a museum. I have a question. Is it possible for a burglar to disable or bypass this tracking system on the artwork?
That's a very, very good question. I worked on the blockchain side, so I think maybe Sanjeev can answer to this question. I don't know, Sanjeev is.
Yeah, of course. Yeah.
Hi, everybody. This is John here from Tyndall. Yeah, great question. It's so I guess at the moment, this is a research prototype. It's possible to design the system to be tamper-proof. There's a couple of ways of doing that. The system itself at the moment is not designed to be tamper-proof, but for example, packaging the system, encapsulating and making it difficult to open the device, to remove the battery. We also have several sensors on the device which we can use to detect if someone is trying to tamper with the hardware. So there's several measures we can take for implementing a tamper-proof system. At the moment, it's not designed to be tamper-proof, but it can certainly be done, yeah.
Yeah, just to add on that, John. So currently we have an accelerometer integrated to the tracking device. So if possible to integrate our system with the security system of the museum itself, for example, then we will be able to raise an alarm in the building if even the thief is trying to move the artwork or the object.
Exactly, yeah. Sanjeev. And we can configure the system to detect movement, vibration to a certain threshold. So yeah, I guess we can put in different conditional checks for things like that. Yeah, so very good question.
Thank you very much. Another question is, what if we have a deactivation of the electricity?
Yes, fantastic question. At the moment, the tag itself can operate, it's designed to operate for years on a single charge of battery. The anchors use more power. They need to be connected to the mains electricity. So if the electricity dies, we still have internal batteries in the anchors that can keep the system operating for several days. So I guess the other thing is most facilities like that would have an uninterruptible power supply. So they would be able to maintain power for a certain duration without power. So I guess if the electricity is not down for more than a week or something like that, our system can work away independently of external power. So I think it would be very rare if this mains electricity would be down for a long period like that. But again, great question.
Yeah. Thank you. Last question. Have you verified whether certain materials or thicknesses might cause interference between the tags and the anchors?
No, so at the moment we are using a enclosure which is made of polycarbonate plastic. So that works perfectly fine. So we have sufficient wireless communication range between tag and anchor. And as long as it's not very lossy material, if you want to use any other material, so it should not be very lossy for radio frequency signals. And of course, we cannot have an enclosure made of metal because that will completely shield the signal between anchor and the tag. So, and I think the majority of cases we'll be using polycarbonate plastic or some other form of plastic. So it should work the way it is working now.
And Sanjeev,
Yeah.
it's a very good question. Sanjeev, didn't we study with Antonio as well several materials that were not possible? Metal is not possible because it acts as a Faraday cage and blocks all the radio signals.
Yeah.
Then most materials like wood, what other materials?
Yeah, we also started looking at biosustainable materials that we, so, currently there are other materials also that we can implement, but we decided for this particular project, we decided to use polycarbonate, which has the loss that is, sufficient enough to, for RF signals to propagate, in a good way.
Yeah, so basically we can use our tag on most materials except metals and except very dense materials like stone or marble or things like that, because they block the signal quite a lot, the radio signals. I hope that answers the question.
Thank you very much. So this was the last question, but if you have any other question, you can write in the chat and we will answer at the end of this event. Matias, if you want to proceed.
Yeah, we can proceed with the more practical phase. This one, I think. Okay, this one. So this is the hashing of the function, and we are going to see all the tools we have here. Let's start from this. On Aurora, okay, we are using NFT, non-fungible token, for the artwork. So whenever an artwork is created, we create an NFT, and we can see this from the history. For example, if we go here, this is the creation, okay, of the artwork, and we can see inside the overview that the collection, the ERC, the token, was created is from a particular and unique collection called Aurora collection, which contains all the artworks inside the platform. Let's wait a few seconds. So whenever an artwork is created, we create an NFT, a non-fungible token. What is an NFT? An NFT is this non-fungible token, is here, okay. Here we can see the collection with all the holders, the total transfer. We can see here some details about the transactions made with every one of these NFTs. And on Ethereum, an NFT is has its own standard. Okay, we have the ERC 721, which is an NFT, an non-fungible token standard. And here we can see the Ethereum improvement proposal, which are made by the community. So the NFT was made by the community as a request. And here are the specifications you must have inside your smart contract to be recognized, marked as an NFT. So for example, you have to add an event called transfer, one called approval for all, some function, for example, transfer to move the asset and so on. So you have, let's say, for example, I want to build a smart contract and create my own NFT. I have to follow this standard recommendation for my smart contract to be recognized as an NFT, for example, by Etherscan or MetaMask. Here, I have to follow this standard. In this case, we have Open Zeppelin, which is a very, very famous and large company working on blockchains that has made some standard based on the specification and recommendation from the Ethereum improvement proposal. They have made some standards. Okay, in this case, we have the ERC 721.sol from Open Zeppelin contracts. They have made all these smart contracts following the standard and the requirements, plus some other function or improvement that have been made in the time. And we can, for example, use this one. We can copy and paste it on any IDE. In this case, for example, we are going to use Ethereum, build it, compile it, and deploy it. So I can simply copy this one, change a few lines, and I have my token, my NFT. Okay, so this is a very good thing made by Open Zeppelin. They have several other type of contracts. Let's say, for example, ERC20, which is another standard, very, very famous, is a token, a simple token that have some decimals because the NFT hasn't decimals since it's a non-fungible token, so it can be only one. ERC, for example, is used for economic purpose, financial purpose, because it has 18 decimals, so it's very, very precise. I can use it as for finance or for creating some funds and so on. And while we have other token standards, we have other interfaces, governance, finance. There are a lot of smart contracts made by Open Zeppelin, which is a standard for Ethereum. After that, we are going to see Remix. Remix, you can go and type Remix Ethereum on Google or your browser. The first one usually is remix.ethereum.org. This one, and you will see probably not the same I will show you because I have already opened it. Oh yeah, this interface here you will see. Now there are some EA integration, so if you click here, you can ask to him some tips to build a smart contract. You have here some tutorials, so you can see it, start coding. And in this case, I have already, leave it. Okay, I've already chosen my contract. Let's start from the beginning. This is Solidity is the language code for create a smart contract on Ethereum. One of the few language code is the most famous one. And for starting it, we have to specify the license. In this case, it's MIT, or it can be a non-license. If we go on, no. In this case, we keep MIT, and we have Pragma Solidity, okay, which identifies the compiler version we have to compile this version of the smart contract because it changes from the compiler. So let's say, for example, why is important to specify this one? Because in the earliest pragma solidity version, let's say, for example, before the 8th. So if I write here 7 or an older one, there aren't any type of control or check on the math operation. So let's say, for example, I have a function that has to do 15 less 30. In this case, it will be minus 15, okay? But if we are using unsigned numbers, it is not possible. But in the older version, this wasn't checked. Now it will receive an error if we try to do this kind of operation. But on the older version, for example, it simply go from the biggest number and removing 15. So it will release a number like this one. So a very, very, very large number with 15. So it goes on underflow. Nowadays, with the latest Pragma Solidity compilers version, we don't have this problem anymore. And how is suggesting here now, the next important thing is using the keyword contract to specify that this file will be a contract, because we have several type of file. For example, I can create a library if I want to add some constants to be used later, or an interface, an abstract. But in this case, we are keep it simple. We want to create a contract, okay? In this case, we call it box, okay? We open and close the not the square bracket, I don't remember now the brackets. We call it in the brackets now, sorry. And we are going to create a very, very easy, let's say, for example, a function that sum two numbers. So in this case is the AI compiler is helping me. I have several types. I have string, address, I have booleans. In this case, I want to use uint, which means unsigned integer, uint to is x, and I will create another variable, which is the two numbers. So this function takes two parameters, the x and the y, and I made it public because this function can be called by everyone. Like I said before, blockchain is public, so everyone can call it. For example, I can put it on private, and in this case, only the smart contract itself can call it. So it will be not visible from outside, but I want to be public because I want to call it from another tool. I call it view, okay, which is a keyword just to say keep it less expensive, since we are not writing anything on blockchain in this case. Returns, and what we are returning, in this case a number, because we have two numbers as input and we are getting one number as output. Here we put the x and the y, we do the sum, the plus. In this case we have warning, which is seeing this as to be pure, so we can change simply this one. And that's it. This is one of the most simple smart contract we can build. We can go here, compile. So once it's compiled, we can see here is ready. And we can, using MetaMask, which is another tool. Let me see, where is the pop-up? Okay. Inject MetaMask, no, it's not. I cannot inject it now. Okay, don't worry. I can deploy it. Okay. Unfortunately, I cannot deploy it on Etherscan, so we are keeping it in a local node. So it is only visible for us in this station. So if I restart the browser, I have the smart contract, but all the data I'm going to write it now will disappear. So once I deployed the smart contract, I've here deployed the smart contract, this one, this box here. Let me see if I can, okay. Here, this one, this is the address of the smart contract, and I have a function. This blue box here is a function, and as you can see here, it takes two parameters, x and y. If I open here, I can see clearly. So for example, I put a 10 and a 5, and I call it. So now I'm interacting with the smart contract. Since it's in a local node, you cannot see it, but we are going to deploy it on a public blockchain on Ethereum. So every one of you can interact with the smart contract. So I call it, and this is the result, 15. And as you can see here, something has been done. In this case, it's a transaction. I'm calling from this address, this is my address, to here we have box.sum, but behind it simply tells this, it calls this smart contract saying we want to call this function, and those are the parameters. And these are some information like on Etherscan. Okay, here is less beautiful than on Etherscan, is probably more chaotic, but basically is the same type of data we have on Etherscan. Let's say, for example, I want to take a transaction here, transaction hash. If I go here, as you can see, input data is as no input data, but you will see something like this one. Okay, so I've made the box, I create my contract, I created this function. We can have some variables as well, because let's say, for example, I just want to use the blockchain to as a calculator. Let's say, for example, I'm using it for track some balance. Okay, I want to track my balance. I go here, I create this type of a variable. Here I'm creating a variable called balance. Okay, I will make it public as well. So I will use, let's say I want to deploy it again. So I compile it. I will check the autocompile flag, deploy it. And here now I have two deployed smart contract. This one is the second one, this one here. As you can see now, we have two boxes, okay? The balance, which is 0, because at the moment we say is a number, the default number is 0, and we cannot change it, okay? So we have to deploy a new smart contract. For that reason, the blockchain is tamper-proof, because I've made this smart contract, I deployed this smart contract, but I don't have made any function to change the balance. So let's change this behavior. So I create a function. Well, get balance is useless in this case, because if we call it public here, a variable, as you can see, it can automatically do a balance here. So it's useless to create a getter function to take it. Let's say I want to update the balance, no? So I will create a function called update balance, a uint 265, which is a new balance, I will call it. In this case, is a public. It cannot be pure, because I'm writing. The pure and view functions can only be used when we are not writing on blockchain, because write on blockchain is expensive. Since, like I said before, every single change on blockchain is tracked by a hashing function and is linked to the next block. So if we write on blockchain, we are asking to change the hash of the next block, and we have to pay a little more to do this type of transactions. So I will write here public. I will not return nothing, and I will simply do balance equal new balance. Okay, so I will remove the older smart contract, is deployed, is compiled, and I will deploy it. I have now a new deploy contract, and now we have 3 boxes, 2 blues and 1 orange. If I click on balance, I can see 0. If I go to do the sum, let's say again, for example, 10 plus 10 equal 20, the balance has not changed. If I want to change the balance, I have to write here, let's say, for example, 50. Look there, here, update, and he is calling transaction is positive, so it's going well. Transaction minded on execution succeed. This is the transaction hash. Some other data. This is how much it costs. And if we go to see how much it costs, let's say, for example, the gas was 50,000 here, which is a nonsense number. But on a view, for example, when we are calling the sum onto the sum, it was 2,000. So writing is very, very expensive, okay? And for that reason, we have to choose very, very careful what type of data we want to store on blockchain. Because, for example, a very large string is expensive. For that reason, we are using a hashing function, which has a fixed length, so we can know how much we are going to pay for updating a transaction, a string, because we have a fixed string. We know that for that string we are going to pay 100. So we have to choose very, very careful what type of data we want to store on blockchain, because it can be expensive to save all data on blockchain. So now I have updated the balance. As you can see here, this is the transaction. So click on balance, and now the balance is updated. Let's say, for example, now my balance is 45. I click on update balance, and I click on balance, and now is updated. So this is how the blockchain works very, very in a superficial way, but this is how it works. This is how we can build a smart contract. In this case, I have here another smart contract, which is a ARC. Now is not getting it, but okay, no, I don't know why is not getting it, but is I will show you just here. To create a, let's say, for example, I want to test, I want to play with the blockchain. I don't have any money. You can do it on a called testnet, what we are calling testnet. So you can test it for free. And you can go on Open Zeppelin, the same company I was talking before, on the wizard. So they have this wizard Open Zeppelin tool, where you have several options. Let's say, for example, I want to create an NFT. So I click on ARC 721. The name of the token, the collection, I want to be Aurora webinar. Let's say, for example, the symbol I want to give it will be RRW in this way, so it changed it here for me. Let's say, for example, I want just to create a new NFT. Okay, so I don't want to destroy NFT, keep it in pause. I can just click on mintable, so allows me to create a new NFTs, auto increment EDS. Otherwise, I have to increment it myself. So the first NFT will be with ID 0. The second one will be ID 1. The third one will be ID2, and so on. Keep in mind that when we are talking about blockchain, basically every language program, we are always starting from 0. So it's 0, 1, 2, 3, 4, 5 to 9. Those are the first 10 number, and not from 1. And let's say, for example, I have some friends, okay? So I want to be able that they too can create some NFT, but just we as friends. So maybe I want to publish it on blockchain, but I don't want a random person create an NFT. I can do a role here, and as you can see, it changed for me the template. And here now I have this role. I can give, for example, to my friend the role of minter, so it can create a new token. But if you don't have this role, you cannot do it. So role, and that's it. I can click on deploy, or if you see here, I can open in a remix the smart contract. Now let's say, okay. As you can see here, this is the smart contract showing before. Is Aurora webinar, the symbol, there is the role, and there are some functions. As you can see, there aren't so many functions in there, but we are going to see it why in a minute. So I want to deploy this smart contract. I want to deploy it. I want to test it. Let's see if now it's working. Yeah, I don't think you can see it, but clicking on here, inject provider, since I have MetaMask, which is another tool to interact with the blockchain, it is asking to me to connect the. No, let me share all the screen so you can see it. Okay, all the screen. Okay, so when I clicked on inject provider MetaMask, it's open a pop-up, this one, asking to me which account, because you can have multiple accounts. I want to connect to Ethereum and to Remix, and I want to connect this one. So I click connecting, is connected. As you can see here, the environment is the MetaMask. So now here to deploy, I have a constructor, so it requires to me to put some data before to deploy it. In this case, the default admin, so which will be the, let's say, the owner of this smart contract, and I will put myself, my address here, and the minter. I can put, for example, my address or my address friends and so on. And I click on transact. Now he's creating the transaction. He's opening MetaMask. He's asking to me to sign this transaction to ensure that I have this access to this account and I have money. I click confirm. And now I have to wait a few seconds because now we aren't on a local node, but we are on a public Ethereum blockchain testnet. And it's done. As you can see, it doesn't take very much time, just a few seconds. If I click and copy this transaction hash, I go on Etherscan. You can do it as well. I put the transaction hash here. I can see some details. For example, the status succeed, the block where the transaction was inserted to, the timestamp, so when the transaction was made 30 seconds ago. My address, this is my address. If I go here on MetaMask, I can see here it's ending on A4B, where what I'm calling in this case is a smart contract. Okay, a smart contract, I create a smart contract, then yeah, here I have some data. And if I click not origin, no, where is the, no, okay, I have to do a further step to be able to read this data, but this input data, look how big this input data is. this input data is simply my address that I put there, here and here, plus some other data. For example, the Aurora webinar, the symbol, and so on. I'm able to see logs, so role granted, because I put my address, and so now I am Inter and I am the admin. Okay, so we can track it. We can see what has been changed inside the smart contract. So before, after, for example, the difference of money I have spent on the storage address and so on. And now I can even interact with it because I deployed the smart contract I have here. See how many functions this NFT has, this smart contract has. Here are only 30 lines, but if we go here, it contains all the other functions I need for creating an RC. So for example, the contract is Aurora webinar, is RC 721 and access control. So it's taking in inheritance all the methods of the other contracts. So we can create multiple contracts and put it together. So I don't have to write a very, very long single smart contract, but I can create multiple files and later combine it. And for example, the default admin, if I click here, is 000. The minter role is this one, the symbol here. This is the symbol, and if I click on copy address, I go here and here. I can see the smart contract here. If I verify the smart contract, which is a very simple solution that in this browser I don't have, I can interact with the smart contract via Etherscan. So it doesn't require to me to go on a remix every single time, but if I verify it, I can interact with Etherscan as I'm interacting with remix. So let's say, for example, I want to mint a token, okay, a new NFT. I want to send it to my address here. So I copy the address, I put here and transact. Now he's asking me to sign because this is a new transaction. See, transaction request. You receive the NFT 0, and this is how much it will be cost to me. So I send the transaction. In a few seconds, I will be able to see here the transaction has been made, or otherwise I can keep track here. See the safe mint, there is this annoying pop-up. But if I click here, I can see safe mint. Okay, this is the safe mint. I can view on the Explorer, which will open Etherscan because it's a standard. And as you can see here, there is token ID 0, Aurora webinar from 000, so is a null address to my address. So it was minted. And as you can see here, this is the input data. I can decode the input data, and you will see simply that is saying that the token is sent to my address. As well, we have some logs. In this case, we have just one compared to Aurora, which for a minting has 9 logs because we want to keep track of several things that are happening under the hood. In this case, we are just creating a simple NFT. And so the transfer, this one, and well, that's it. That's it. Is a very, very easy and superficial way to look at blockchain, how it works, how smart contract works, how to create a very simple smart contract. So if you want to try, test it, you can check Remix, or otherwise go to Open Zeppelin Wizard and try to play here with some to create some cool contract. If you have any question regarding what we are seeing here about blockchain in general, please ask. So we interrupt here.
Wait just a moment to see if anyone has any question. I don't think so. No question in the chat. So I remind you that this event will be online next week on Aurora project website. So if you want to see it again, or if you want to share it with someone that couldn't join today, you can do it for sure. I remind you also that Aurora is on LinkedIn, so please, if you have not done it yet, follow the project so you will be updated also with the other events we are going to organize. For example, we will have an amazing training school in September in Serbia, so stay updated with our news, and if you can and join us in our training school. And I think that no questions. There are no questions, so I think that we can close this this event, this webinar. I would like to thank the speakers that have been part of this event today, but also all the people present here. So many thanks for joining us, and thank you very much. Have a nice day.